Hi class, and welcome back. In this video we're going to talk about data transfer instructions. Data transfer instructions. And to set up this topic, let's do a little bit of a drawing here. We had previously talked about registers, particularly CPU registers. And one thing to note about our CPU registers is, as the name suggests and tells us, is they are actually part of the CPU. Right, we've got our register file, right? Here it's part of the CPU. Okay, meaning that they're exceptionally fast. Then they operate at the speed of the CPU itself. And we're going to look at this in relation to memory. And we have seen in the prior video about how there's many different levels of memory, this so-called memory hierarchy. And here I'm just going to kind of condense that into one single unit, one single block. We can actually even call it data memory. We're just going to assume that this is all other memory that's not the CPU. So we're making an assumption here. We're simplifying the problem, right? Managing the memory hierarchy itself is a very complicated topic that goes outside the nature of this course. So we're going to make some assumptions here, and that's why we're just going to have our registers and our data memory, okay? And what we're going to see is that we want to learn how to be able to store information in data memory, okay? We've already learned how to store, read, write, manipulate information in the registers, okay? And we're going to do that with two instructions, okay? We're going to have one instruction that goes from the register and stores it into memory. So this is a store instruction, right? Takes a value from memory and puts it in, it takes a value that's in a register and stores it in memory, okay? We're also going to look at instruction that takes information from an address in memory and loads it into a register, a load instruction. Okay. Here's a key point. Okay, the CPU can only manipulate data that's in a register. Okay, it can only perform operations on data that's in registers. By operations, I mean if you're doing add, subtraction, shifting, anything like that where you're manipulating information, okay, it has to be in a register because the registers are fast enough for the CPU to operate on them, okay? This here is fast. This here is slow in comparison, okay? So the CPU, right, operators operates on registers. Okay. So ignoring the typo here, it doesn't really matter. CPU operates on registers. Okay, that if all I can do with memory is take some information and say, hey, store it away in memory. Okay, or grab some information in memory and put it in a register. Okay, so if we want to like add something that's in memory, we have to load it in a register, add information to that register, and then store that information back. And we'll see examples like that. Okay. All right, so this is our two instructions that we're going to kind of dive a little bit deeper into. Okay. It's a little bit summarizing what I just saw in the previous, that I drew in the previous slide. Here's our load instruction. Okay, it will take this register will get the value that's stored in the memory address. Okay, we're going to assume we're going to load 32 bits, right? 4 bytes because that's how big our registers are. Okay, we're going to go to the memory address, grab those 32 bits there, those 4 bytes, and load that into this register. So this register gets written to. Store goes the other direction. Store is going to take that information that's in the register and store it in that memory address. Okay, so these are the two new instructions that we need to learn. Okay. All right. So let's think about this, right? Just to kind of recap what we saw in a previous video really quickly, right? We have very, very small amounts of registers. They're very tiny. We have 32 registers, right, that we've been using for most of our examples, right? We've also seen it as 16, but any way you cut it, it's a very small amount. Memory can be much bigger, right? We're allowed to address, okay, right? The max limit is we can address 32 to the 32 bytes, okay, 2 to the 32. It's a very large number, okay, 2 to the 32. And that's because if we're dealing with a 32-bit architecture, right, we're going to see how we're storing addresses later on, right? The biggest address that we're able to store in this example, okay, is something that is 32 bits long for an address, right? The address is effectively a pointer, and what we're going to imagine is our pointer can store an address that it has 32 bits to store an address, which means if each address is a byte, a single byte, that means we can store 2 to the 32 bytes. We can address 2 to the 32 bytes, okay? Right, a quick little analogy of that is that, you know, you can imagine you're on a road, right, and you've got houses on the road, okay? And let's just say for whatever reason you only have 3 digits that you can store for the number, that you're not allowed to go beyond that in this made-up example, right? That would mean that your limit for how many unique homes you can store would be from 0 all the way to 999, right? In base 10, you'd be able to uniquely address 1,000 homes. Okay, it's the same idea down here but instead of homes, each home is 1 byte. Okay, and we're dealing with powers of 2. All right, and we have 32 bits, right? 32 bits. Which means that if how many bytes we could uniquely address would be 32. Would be 2 to the 32 unique addresses. Okay? Right. This is very important because just kind of showing a little bit of an analogy that we've kind of looked at something similar already, but I'll just kind of briefly recap. These registers are really small, really, really small. Right, we only have, let's say, 32 of them. So imagine this chef here. We're going to use a kitchen example. Let's imagine this chef is our CPU, right? And the chef is making a meal, okay? The chef only has a small amount of space, like counter space, right? Very small, but fast. Not fat, but fast next to him, okay? To be able to store things in this little counter space, okay? But there might be all sorts of other ingredients that the chef needs. Let's ignore cache memory for a second because it's like a similar idea. Right, I'm just going to ignore this. Let's imagine, right, chef only has a small amount of space nearby, right? So if the chef needs additional ingredients, it goes to a larger but slower access over in the pantry, right? Takes more time to kind of dig through and find stuff. It's further away from where he's operating, right? So it's the whole goal is to try to keep stuff that's needed. Short-term stuff should be here, okay? Longer-term ingredients here, right? You only have a certain amount of space to store things, right? So the things that you need readily available should be on the counter, and stuff that you don't need right away, you can have in the pantry. You can come grab them when you need them. Okay, that's the same idea when it comes to dealing with registers in memory. Okay, you keep the stuff that you need right, basically in the CPU, right where you're working. Okay, so we've had this question before, And I give a very brief example when students ask this, because we kind of don't really do it justice answering the question till now, is, well, wait a minute, we only have 32 registers, or a very small number of registers. What do we do if we're storing more than 32 variables, right? That makes perfect sense. It's a very good question. And the example, what we do is something called spilling registers, right? Where if we've got our CPU, we've got our registers, okay, we've got our memory, okay, we're going to take the variables that we don't need right away, right? We're going to take the ones that we don't need right away, and we're going to store them away in memory. Okay, so the longer term stuff is here, and the shorter term stuff is here, right? So we can have a very large number of variables, right? We can store 2 to the 32 different addresses, right? So if we're storing everything in words, right, 32 bits, that gives us 2 to the 30th different words to store. It's a very large number. Okay, we can have them out in memory. We can store them away, right? And we just have to keep the variables, right, the information that we need in the short term in the registers, okay? So we do have it's not like we're limited to that very small amount of data that we can operate on, okay? Quick little example. I don't want to get too bogged into this one because we're looking at some code here and it's a selection sort algorithm and we don't really want to trace through it because it's not really the point. But I just wanted to kind of illustrate this point with some real code. This code is a sorting algorithm, and it also determines the smallest 2 numbers that are in an array. Okay, the smallest 2 numbers that are in an array. I show this example. I've used this in a class before for people kind of solving a problem doing that in an intro class. And so we're kind of looking at it in a different way to illustrate this point. If we're sorting it, right, let's just imagine that for whatever reason we initialized these 2 variables at the top, smallest 1 and smallest 2, okay? They are not used until down here, right? They're not used, and we've got 2 for loops here doing a n squared operation, right? If we're looking at it in terms of big O, we're not using it during all that entire algorithm, those loops. Those smallest variables are not used, okay? So you can think about it in terms of what the CPU needs to know. The CPU, right? We do not need to have smallest 1 and smallest 2, right? When we get past initializing them, okay, those numbers can be stored away, right? It's kind of like putting them away in the pantry. Put them away, store them away during this entire run until you get down after the loops, right? And we need to, and we're doing something with them again. Then we would want to bring them over back into the registers, okay? Because we're actually using them readily, okay? That's called spilling registers, right? And it's a very powerful topic that comes up in other courses, right? If you're doing something like an operating systems course, there's a very similar thing that you kind of go through and learn in terms of managing the memory hierarchy to be doing that. Okay. All right, so let's go further. Right? We've talked about these load instructions and the store instructions. We introduced those a moment ago, right? We say that a load is going from a memory address and taking it and writing it to a register, where the store is going from a register, reading the register, and writing it to a memory address, okay? But we didn't really talk about yet is how are the memory addresses determined, okay? Now, I mentioned this a little bit, but didn't really go in a lot of detail, okay? What we want to remember is that computers work where the smallest amount of information we can address is a byte, right? This is a convention, it's a standard. It's something that you can imagine building systems that are different, but effectively there's a trade-off, right? If you have an address, for instance, address 0, Okay, and then we have the information or the values. Okay, if it's 1 byte long, okay, that seems to be a nice trade-off between this being a reasonable amount of data, but also granular enough, right? If you had every address be for every bit, you would restrict your address space so much, right? Because we have, right, if we had 2 to the 32 addresses, right, and each address is 1 byte, right? Then we can uniquely address 2 to the 32 bytes, right? However, if each address was 1 bit, you would be addressing 2 to the 32 bits. You'd cutting your address space down to 1/8 of the original size, right? So there's a trade-off, right, to be addressing something that's very granular versus addressing, having that level of control versus restricting your address space. Okay. So the standard is it's 1 byte long. Okay. So if we have a number, an integer that's 4 bytes, we actually take up 4 addresses. Okay, that's a key thing to remember. Right? If you have an integer that's 4 bytes long, you actually take up 4 address locations to store 1 integer. Okay. So that's a key point, right? So let's look at the ramifications of that. Right? Oftentimes we operate on a so-called base address. I'm going to call this is called the source address. I'm going to refer to it as the base address. Okay. And then some sort of, I'm going to call this here the offset. Okay. Think of an array. It's kind of like what I had drawn on the previous example. Let's imagine we have an array, int array 10. Okay. The location that array starts in memory, okay, this starting location would be the base address. Okay. That's basically a way to think of that as the address of the first index of the array. Right? If you remember the notation for pointers, right, the address of the first location in the array is the base address. Okay? The numbers are sequential. So if we have A1, address of A2, etc., if this is our base address, which is effectively the location, the address of A0, okay, and then the next location is the address of A1. We got the address of A2, etc. Right? Eventually, we've got the address of A9 because I said it's 10 long. These are all sequential in memory. Arrays work that way, and they make a nice example. Okay. The index. Here's usually what we refer to as the index. Right? So the index could be 0, 1, 2, all the way to 9. Okay. However, the memory address, okay, the memory address itself okay, this is the base address, right? The memory address itself, let me use maybe a different color here. The address is really going to be for each one of these, right, is the base address okay, plus, right, the base address plus the index times 4. Okay, with this being the index. Because we want to remember, in reality, these are all 4 bytes long, right? If this is byte 0, this is byte 4. This is byte 8. Okay, these are all 4 bytes long. Each address is 4 bytes. So we better, if we want to address the right thing, we better multiply it by 4. Okay. Now, this first one, the index is actually 0, so this term drops off, and it's just the same as the base address. But when we look at this here, right, this location, okay, that's going to be the base address, okay, plus the offset, I'm sorry, not the index, right, times 4. The index is 1, so this is effectively plus 4, right? It's the base address plus 4. The next one, the index is 2, right? 2 times 4, 8. 8 plus the base address, right? So if this is the base address here, we're going 8 addresses over, 8 bytes over, okay? All right, this video is starting to get a little long. I'm going to stop it here. We're going to follow up on the next video to show an example where we start using those load and store instructions to compile some piece of C code into ARM assembly and see how it works and get a better feel for it.